Welcome back, everyone. This is part 2 of our first set of notes on exponential functions and expressions, okay? The third page of your notes, you can see I've reproduced them here. They are mostly for reference. This first table is really just to build some number skills here. My expectation is that these values in the table are values you're comfortable seeing, recognizing by sight. Your powers of 0 are always going to be 0, your powers of 1 always 1, and then we go from there. If you need to pause here and fill in the table, you certainly can do so. I think it's worth going through the process yourself and filling these in, even without a calculator, right? Just going through the process and multiplying these out is worthwhile just to start, continue kind of remembering these and getting them into your brain one way or another. So the next part of this is a refresher on our exponent rules. We're going to use these extensively throughout the unit. Exponent rules, we can see here we have quite a few of them. The few basics. When I multiply a common base, all right, a to the m times a to the n, we add their exponents, right? We did that write it out work, but if I think about this, 3 to the second is 3 times 3 times 3 to the 4th. I end up with how many total 3s? Well, it's 3 to the 6th power. The same logic applies, just we're dividing. When I have a common base and I divide, as you can see, a to the m divided by a to the n, I subtract their exponents. Same logic, as you can see, basically the terms in the numerator and denominator cancel one another. In that process of canceling, we are reducing the number of repeated multiplications we're seeing. Our third property is negative exponents. Negative exponents create reciprocals. They do not create negative numbers. Anything to the 0 power is 1. As long as a does not equal 0, that would be 0. This is what we also call this is what we call the power rule. Both 5 and 6 are kind of flavors of the same thing. The one power rule we tend to use more is number 6, where we raise a power to a power, right? If I had, x squared to the 3rd, that's really x squared times x squared times x squared, or x to the 6th. I can get there quicker by multiplying those quantities together. The 5th rule, just to jump backwards here, is basically that if I raise a product to a power, each of the factors that are being multiplied, a and b, are also can be thought of as raised to that power. A times b all to the m is the same as a to the m times b to the m. This power rule also applies to fractions, so that if we have a fraction raised to a power, we can raise that both the numerator and denominator to that exponent. And finally, if we were to square an absolute value, that is the same as squaring the number and then taking its absolute value. Both have the same effect on a number. Both will create a positive number. Last note here, make sure that if you're using fraction exponents or rational exponents, we use enclosed parentheses if we have, if our calculator requires it. We can cause some issues with order of operations. So when in doubt, if you're raising a power to a fraction exponent, put parentheses around that exponent. So we're going to take a look at some kind of complexity that we see and areas for common mistakes with negative exponents and fraction exponents. So here you can see on the last page of our notes, the definition of x to the negative first is that it's 1 over x to the positive 1. But again, we just have to be careful. So here we can see in example 1, we have negative 2 times x to the negative 2. And what we need to pay attention to here is the lack of parentheses. In this case, this x to the the negative 2 only applies to the x. So this is the same as negative 2 times 1 over x squared. So if we were to simplify this, we would end up with -2 in our numerator and x squared in our denominator. In order for that -2 to apply to the coefficient, we would need parentheses here, which clearly are missing from the original problem. If we scroll over to example 2, we have 1 over a to the -2 minus b to the -2. And the common error, just don't do this. Just want to make this clear that this is not our notes. This is a common error, is that people will say this is a squared minus b squared over 1, and they'll say that it's done. That is incorrect. It's incorrect because exponent rules are all about multiplication. We are repeatedly multiplying or dividing, right? It's inverse. And in this case, that subtraction really throws us off. What this expression really says, let's cross that off, is that it's 1 divided by a pretty complicated fraction, 1 over x squared minus 1 over b squared. So if we wanted to simplify that, first we would want a common denominator in our denominator. So this would be the same as 1 over b squared minus a squared over a squared b squared, which we can multiply by the reciprocal and get a squared b squared divided by b squared minus a squared. We can see that that's clearly not the same as a squared minus b squared. Understand that things get complicated when we add or subtract with exponents because we are no longer just dealing with our exponent rules. We need to think about how these exponents are affecting our order of operations. We also are going to do some factoring in this unit, right? But the factoring we're going to see here is a bit more complicated as you can sense that pattern. As you can read, factoring has always involved an understanding of exponent rules, but as often happens, especially in math, the process becomes routine, and then when things change, the non-routine takes much more concentration and creative thinking. So what are we saying by that? Well, this looks complicated. That's the non-professional opinion here. We have 4x to the 3/2 minus 2x to the 1/2. Well, we can factor here. We can factor a common 2x to the 1/2. I chose 1/2. That's our smallest common exponent that these two terms have. And what we'd end up doing is multiplying this times 2x, right? If we were to multiply 2 times 2, we'd get back to 4. X to the 1/2 times x to the 1 would get us back to the 3/2. And then factoring out a 2x to the 1/2 from 2x to the 1/2 would leave us just with 1. Well, this is an inequality, so having this as a as a product where we have factors times one another makes this much easier to deal with. Just like we did last unit, we can test our intervals. We can test to the left of our 1x intercept. Really, we have to deal with, and we can put this on a number line, 0 and 1/2. Our test points, we could say, are -1, positive 1/4. Let me just erase that little sign there. And then let's say 10. Let's use 9 just because we're going to take a square root, and that'll make life a little bit easier on us. What we're seeing here, do these values make this inequality true? Well, if I were to plug in -1 here, I would have the square root of -1, which is undefined. So this would not be part of a solution for our inequality. If I were to plug in, say, 1/4, I would end up with 2 times 1/4 to the 1/2 power, which is the square root of 1/4, or 1/2, times 2 times 1/4 minus 1. You can see it gets a little messy in there, right? So once we multiply this out, we'd end up with 1 times negative 1/2. And again, this interval here between 0 and 1/2 would not make the inequality true. We can test a larger value, let's say 9. We would get 2 times 3, right? We know the square root, or 9 to the 1/2 power is 3, times 2 times 9 minus 1. We work through this with our order of operations. We end up with 17 times 6, and we can see that's going to be a positive number. So this part of our inequality would work. Our solution to this inequality was found the same way we've always done it, right? The way we solved polynomial inequalities in Unit 2. However, the factoring we did involved fractions in our exponents. All right, let's look at example 4. Again, we have kind of a mess here, right? We have, a quantity raised to a negative exponent, -3, and that same quantity raised to a -4 exponent. Well, what we can do is we can factor out the least common factor of these two terms, which I'm going to say is 2x minus 1 to the -4. When we factor that out, we are left with 2x minus 1 to the positive first power plus 2x minus 1 to the 0 power. We can simplify this. Well, this expression here will be 1 over 2x minus 1. Let's get rid of that outside parenthesis. Raised to the positive fourth, and that's being multiplied times 2x minus 1 plus 1, or just 2x. So our fully simplified form would be 2x divided by the quantity 2x minus 1 to the 4th power. There we have it. So we took out the smallest exponent shared by these two terms, which was -4. Now, usually we choose a smaller number, but when our exponents are positive, that may make some more intuitive sense. By factoring out that -4, we turned this exponent positive, and we turned this exponent into a 0. And using those properties of exponents, it makes these expressions easier to make sense of. All right, our last section here is going to be solving equations involving exponents. So we're going to solve for x. It's based on the idea that if we have common bases, right, a to the n and a to the m, then m and n must be the same, right? A common base, if it equals another expression, well, it must be raised to the same exponent. So in this case, I would rewrite the left-hand side as 2 to the 6th power. And I would rewrite the right-hand side. Well, I can rewrite 2 with a base of, I can rewrite 4 with a base of 2. In this case, I can rewrite 4 as 2 to the 2nd, and that quantity is raised to the x power. I can use my exponent rules, say 2 to the 6th equals 2 to the 2x. Now my bases are the same. 6 equals 2x, so x equals 3. We have another example in example number 6. In this case, we have 1/4 raised to a power and 32 raised to a power. Now these two don't really work directly compatibly, but we can rewrite each of them with a base of 2. I can rewrite 1/4 as 2 to the -2, and I can rewrite 32 as 2 to the 5th. Right, knowing those exponents, recognizing 32 and 4 as powers of 2, makes this process a lot easier. When I multiply these exponents, I have that common base, so I'll have 6n equals 5 times n minus 2. I can distribute on the right, get 5n minus 10, so n will equal -10. We can keep moving on to number 7. In this case, because our base is x minus 1, I think I'm going to avoid that process of common base, but I'm going to just work with some of the rules we've seen before to solve for x. First thing I'm going to do is I'm going to divide both sides by 2. And then I'm going to rewrite this in a form that we like. 1 over x minus 1 quantity squared equals 1 over 16. Why would I make that step? Well, I just really don't much care for negative exponents. What we've really created is we've created 1 over a number divided equals 1 over a different number. So we could say that x minus 1 squared is the same as 16. Well, now I just have a quadratic to solve. I could take the square root of both sides and solve for x. So x could be 1 plus or minus 4. And if we want to simplify that, x would equal 5 or negative 3. Last one is definitely one we want to use our calculator for. We have 3 times x to the 2.73. Well, we're going to work backwards. We're going to use our inverse operations. We're going to divide by 3. So we'll have x to the 2.73 equals 11 thirds. Now, there's a couple different ways we can approach this. We can either, we want the exponent on x to be 1. So the couple different ways we can approach this is either we can take the 2.73 root of x to the 2.73 and do the same thing on the right side of our equation. That can be a little trickier to enter into our calculator. The other thing we can do is we can raise to an exponent both sides to the 1 over 2.73. These have the same numerical value, where they're going to do the same thing. In either case, we're going to get a final solution here of x equals 1.61. So even when things get complicated, we can still lean on all those exponent rules we saw in Algebra 1, Algebra 2. We're going to use factoring. We're going to use what we know about rebasing things. We have to be comfortable moving between these different techniques as we go. Thanks, guys.